All right, so we can turn that on so we can see a little better. Continuing on through P7, we're about 3/4 the way through, so working out well. Starting off here with kickoff of what is a rational expression? Well, I think a rational expression is a quotient of polynomials. So by quotient of polynomials, think polynomial over a polynomial. So fraction, I'll put that in parentheses, fraction of polynomials. So polynomial over polynomial. But continuing on, we're going to be now, last time all we were doing, we were working with different polynomials, simplifying them down. Well, really, we've been doing that the last few lessons here. Now we're actually going to be solving these out. So we're actually going to be working with equations, starting here with a linear equation. So basically, it can be written in the form of ax plus b equals 0. So think we have a single variable, no exponents involved. So when we're solving a linear equation, you want to simplify the algebraic expression on each side by removing any grouping symbols, combining like terms. Get all the variables on one side, all the numbers or the constant terms, the numbers on the other side. Get the variable by itself, solve. And then you want to check that solution. So for example, if we're going to solve this, so first thing I'm going to do is I'm going to distribute my 2 in here and get 2x minus 6 and then minus 17. The other side here we have 13 minus, well, negative 3 times x would be minus 3x. Negative 3 times 2 would be a minus 6. Now, something we can do with this is if we have the same thing on both sides, they're just going to cancel out. Because I would add 6 to the other side, and adding 6 to a negative 6 would cancel out and be 0. So that simplifies it down a little bit. So now I'm going to look at, okay, I want to get my variables on the same side. This one's positive, this one's negative. So I want to have a positive set of variables. Now, it doesn't matter. We just divide by a negative to get the variable by itself, but it's a little nicer to do it this way. So we get 5x on this side. I'm also going to add the 17 over. So that cancels. And 13 and 17 make 30. So if I divide by 5 then, x would equal 6. Okay. Now, I could have gone the other way where I subtracted the 13 over, subtract the 2 over, and I would divide by negative 5, which would have been negative 30 then. You still would have get 6. So it doesn't matter which way you do it. Going to get the same thing in the end as long as you follow those order of operations. Now to check it. So what you do is you put that answer back in for the variable x, what we solved for, and then see if we are equal on both sides. So here, 6 minus 3 would be 6, or 6 minus 3 would be 3, times 2 would be 6, 6 minus 17 would give us a negative 11. The other side here, 6 and 2 would be 8, 3 times 8 is 24, 13 minus 24 would be a negative 11. So it works, so we're good. Now, if we are dealing with linear equations that have fractions involved, so we need to either find a common denominator, or another way we can do this, and I feel this is the easier way, and I'll show you here, is to go ahead and just times by whatever that common denominator is on both sides, and it'll get rid of the denominators, and then we just are back to a linear equation. So 4 and 3, I'm going to times both sides by 12. So what's going to happen is this. So on the first one, I could divide it by 4, and I would have 3 times the x plus 2 left over. On the second one, I would reduce by a 3, and I would have a minus 4 times x minus 1 left over. The right side, I just have 24. So what I'm talking about here is if I have 12 times my x plus 2 over 4, I would reduce this to a 1 and this to a 3, which is why I have my 3x plus 2. That's where I'm getting these from. And I would do the same thing here. Only this time dividing by 3, I would have a 4 left over, which is why that's in front. So, distributing this in. 3x plus 6 minus 4x plus 4. Negative 4 times the negative 1 plus 4 equals 24. So, like terms together, 3x and a negative 4x would be a negative x. 6 and 4 would be plus 10. So if I subtract the 10 over, I have negative x equaling 14. And so then that would just switch to mean x equals negative 14. Move the, basically you divide the negative or times the negative over, either way works. And it would switch over to the other side. Now, if we went through and checked, negative 14 plus 2 would be negative 12. Negative 12 over 4 would be a negative 3. Negative 14 minus 1 would be a negative 15. Over 3 would be negative 5, but it's subtracted, so it would be a plus 5. And negative 3 and 5 would equal 2. So that works. Now, rational expression. We talked about last time was where we had a polynomial over a polynomial. Well, if we have a rational equation, now we have two or more, or one or more, I should say, rational expressions being involved in an equation where we have an equal sign. So last time we just did something like this, where we had just two rational expressions added and we simplified. Now we set them equal to something, and we're gonna have to actually go through and solve the whole thing. So first thing we're gonna do is this. Factor this bottom. Well, we'd go to x and x. Negative 12 would mean 1's plus, 1's minus. And we have to have a positive 4 out of this. So I'm going to say a plus 6 minus 2. Now, a lot of times they should be what are on this other side. Won't always be, but a lot of times it will, so that they work out really nice here. So if I times both sides by this, well, on this right side, that's all gone, and so I'm just equal to a 4. The left side, this first one, the x plus 6's would cancel, and so we would have 3 times x minus 2 plus. On the second one, the x minus 2's would cancel, and so I'd have 1 times x plus 6. Okay, so same thing as what I just did on that last equation. So by timesing by that common denominator, it gets rid of the denominators, makes it into a nicer equation to work with. And then we solve it out like we've been doing. So distribute the 3 in. So 3x minus 6. Distributing 1 in would just be plus an x plus a 6 equals to 4. Well, plus 6 minus 6 on the same side would cancel. 3x and an x would make 4x equaling 4. And if I divide by 4, x would equal 1. Now, something you got to keep in mind when you're dealing with rational equations is those exclusions. Well, what could x not be in this case? Well, x cannot be a negative 6 or a 2. And it'd end up being the same thing on this side. So you always have to think about that with your what you equal out here. So negative 6 and 2 isn't what we got. So, hey, this works. This would be an answer we could go with. Now, if it up here, if it would have been, say, negative 1 is one of these that it couldn't be, or I should say positive 1 since we got 1. So if your answer is one of those exclusions, then it would be the empty set, because that doesn't work. It's no solution. Now, this one isn't, so it works, but that's something you always have to keep in mind. So, next one here. So, x squared minus 1, we factor out to be x minus 1, x plus 1. Well, that fits the other side, so if we times by that on both sides, well, this whole bottom would cancel, and the x minus 1's would cancel for this back one. Here, the x plus 1's would cancel. So we'd have x minus 1 equaling 2 minus, and 1 times that. X plus 1 would just be a minus x minus 1. Because even though it's x plus 1, we're a minus 1 here. So that has to distribute through. Okay. So we have a minus 1 on both sides. I have a negative x, so I would add my x over. So x and x would make 2x equaling 2, which dividing by 2, x would equal 1. Now again, if we think back to those exclusions, what x cannot be, well, x could not be 1 or negative 1. Well, we got 1. So in this case, even though we got a solution, it can't be that, or it'll cause problems. So that's where this one's a no solution. So that's something you always have to keep in mind when you're working with rational equations. When you have x's on the bottom, you have to think about those exclusions. What can x not be? Is it one of our solutions? Do we have to get rid of one of our solutions? Now, there may be times and we're going to work some of these in the future here, where say we're dealing with an x squared or an x cubed where we get multiple x's for answers here for solutions. Well, if one of those is one of our exclusions, we would just cancel the one, but it'd be the other two. We would still have solutions. It's not that, hey, as soon as we have one, that's not it. It's a no solution. It's just that solution itself doesn't work. Now, we can also go through and solve formulas for a specific variable. So let's say we want to solve for p here. We want to get p by itself. What would p equal in this case? Well, our common denominator here is pqf. So if I times it by each one, the first one, the p's would cancel, and I would have qf on top. Plus, here the q's would cancel, and I would have pf on top. And lastly, the f's would cancel, and I would have pq on top. So already this easier to work with than this, dealing with the different denominators there. So you need to get p's on the same side. So I'm going to subtract the pf over. So qf equals pq minus pf. Now from there, we're going to pull the p's out. So qf would equal p parentheses q minus f. So distribute property in reverse order there. And then we're going to divide out the q minus f. So in other words, p is going to equal qf over q minus f. And that'll be our solution there. Now, if we're working with equations that have absolute value in it. So first off, you have to keep in mind is absolute value always has to be a positive solution. So if you ever have absolute value equaling a negative here where the c is, that's going to be a no solution. That one won't work. There's no way to have an absolute value equal a negative. It always has to equal a positive. Now, as long as it's a positive, then we're going to split it into two equations. One where it's a positive answer, one where it's a negative answer. Because since the absolute value always turns it positive, we could get a negative inside here, but then that'll flip it back positive when we take it out of the absolute value. So to solve here, first we got to do is we got to get down to just absolute value on that side. So anything else we need to get rid of, starting with, I'm going to add 15 to the other side. So 5 absolute value of 1 minus 4x would equal 15. Now I would divide by 5 and get the absolute value of 1 minus 4x equaling 3. So here's the critical point. So we have just absolute value on this side equals a positive, so we're good to go. So now we break it into two different equations. So 1 minus 4x equaling negative 3 and 1 minus 4x equaling positive 3. And then we can go through and solve. So if I subtract 1, I have a negative 4x equaling negative 4, and divide by negative 4, I'd get x equals 1. Over here, same thing, subtract the 1, so negative 4x equals 2, dividing by negative 4, x would equal a negative half. So a lot of times here when we get multiple solutions, you might also see it where it's written as a solution set. So just a couple different ways you might see it going forward. Now, if we get into quadratic equations. So a quadratic equation is in the form of ax squared plus bx plus c equals 0. So we're going to be dealing with an x squared, possibly an x, possibly a constant, but we want it in this form. So what we're going to do is it's called the zero product principle, which says that the product of two algebraic expressions is 0, then at least one of those factors has to equal 0. So using that idea, which makes sense, if we're multiplying two numbers and we get 0, one of them or both of them have to be 0 is what it's saying. So if AB is 0, then either A is 0 or B is 0 or maybe both. So we use that to solve quadratics. So the first thing we're going to do is we're going to try to get it in this general form by getting all the terms on one side and getting a 0 on the other side. Then we'll factor it, we apply that zero product principle, and then we solve each one for x, and then we check our solutions. So, solving this here. We're in that form, everything's on the same side. Now, I know we don't have a constant, but that's okay. The main thing is we have an x squared. So, factoring it first. When we factor, we look for a common factor we can pull out, which would be a 2x. So if I pull 2x out of here, I'd have a 2x left. If I pull a 2x out of there, I'd have a 1 left. And then I'd set each one equal to 0. So if I divide by 2, x would equal 0. I would add the 1 over. So 2x would equal 1. Divide by 2, x would equal 1/2. Now, way to check it, if I put 0 in here, it would be 0. Put 0 in there, it would be 0. 0 minus 0 is still 0. So that works. If I do a half, 1/2 squared is a fourth. 1/4 times 4 is 1. And 2 times a half would be 1. 1 minus 1, still 0. Okay. So that's the check that you can do with that. Now, if I have the problem u squared equals d, well, one way to look at this is I would do subtract the d to the same side. So u squared minus d would equal 0. Now, typically, when we have two terms with a square here, we're going to do a difference of squares. So we're going to rewrite this as u squared minus the square root of d squared. So that when we factor it, we would get u plus the square root of d and u minus the square root of d equals 0. While setting each one equal to 0, I would get u equals a negative square root of d and u equals a positive square root of d. So you might be going, well, why did we do it that way? Well, the reason why I did this is I just want to show you why when we do this, we get u equals plus or minus the square root of d when we do the square root up here. So if I would have right off the bat, if I square rooted both sides, yes, that cancels and we get u equals. But over here, we can't forget that it's actually a plus or minus the square root of d because we get two different answers when we do that, when we solve this all out for u. So that's why we do the plus or minus in front of the square root when we solve them. So always include that in there. So what that's called is the square root property. So u is an algebraic expression, d is a positive real number. U squared equals d has two solutions. So the positive square root of d and the negative square root of d. So plus or minus the square root of d. That square root always will have a plus or minus when we're solving them out. So like here, we would have 3x squared. I'm going to add the 15 to the other side there. I'm getting ahead of myself. So 3x squared equals 15. I'm then going to divide by 3. So x squared would equal 5. And it's at this point that I can go, okay, I'm going to square root this side, square root this side. So x would equal plus or minus the square root of 5. And I have my solution. So if you think about it, when we're doing this, however many x's to that exponent, whatever the exponent is, that's how many solutions you're going to have. So x squared needs 2 solutions. Back when we had x, we only got 1 solution. Here, x squared, we need 2. If that was x cubed, we'd have 3. X to the 4th, we'll have 4. Now, some of those may repeat or may get into imaginary numbers, but that's something for later on. Now, one of the things that you may have to do when you're solving, so when it's in the form of x squared plus bx, you may have to use completing the square. So what happens is we take half of this middle term and we square it, and we add that into each side of our equation. Now what that allows us to do is makes this into a perfect square. So, looking at this, normally we would go, oh, it's a trinomial. We would do 2 sets of parentheses. Well, if this is positive, we look at the middle and they both would have to be negative. So factors of 4 in order to get 6. Well, factors of 4 would be 1 and 4, which would add together to be 5, or 2 and 2, which add together to be 4. Either way, we can't get a 6. So that's where factoring it normally won't work out. So that's why we have to do completing the square here. So what I'm going to do is this. I'm going to subtract the 4 over right off the bat. And so I'm going to have x squared minus 6x. I'm going to leave a space and I have a minus 4. Here's why. So half of this middle term, so negative 6 cut in half, it's going to be a negative 3. So I'm going to add negative 3 squared to both sides. Now, reason why I'm writing it like that. So when we make this perfect square, it's going to be the first term that's squared, the last term that's squared. So if it's a minus 3, we're a minus 3 here. And that's the perfect square in this case. Now, on this other side, we're going to FOIL it, or not FOIL it, multiply it out. Negative 3 squared would be 9. 9 and negative 4 make 5. So that's the completing the square part. Now from here, we're going to solve for x. So we would square root both sides and get x minus 3 to equal plus or minus the square root of 5. And then we would add the 3 over to get x equaling 3 plus or minus the square root of 5. So that's how we solve using completing the square. So completing the square was getting it to this point, and then we have an equation we can solve from there. Now, generally, I don't have you guys do completing the square, because while doing completing the square, they figured out a formula, which this is all the steps to it. And I believe it was the Egyptians back in 700 BC, maybe. So, been around for a while. So clearly they're like, hey, there's an easier way to do this when we're doing all this math. Well, it might have been 80. I take that back. I'm pretty sure it's 80 now that I think about it. Either way, still, long time ago. But they obviously didn't have calculators to do all this, so doing this all by hand, they're like, hey, there's got to be an easier way. Found this pattern that, hey, this is what it ends up being, so then we can just plug in numbers and solve from there, instead of doing completing the square. And it's called the quadratic formula. So, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So, where it comes from is, when we have that ax squared plus bx plus c, we're able to pull out those coefficients. So like, for example, here, a is what's in front of x squared, b is what's in front of the x, and c is the constant. Now, since it's minus 8, this is a negative 8 for the b, so keep in mind there. So when I set this up, x equals negative of a negative 8 plus or minus the square root of negative 8 squared minus 4 times a, which was 4, times c, which is 1, all over 2 times a, which is 4. Now, to simplify from here, negative of a negative 8, those cancel, and it's 8 plus or minus. 8 squared would be 64. Negative 8 squared, same thing. Minus 4 times 4 would be 16 times 1, still 16. Bottom 2 times 4 is 8. So if I go a little bit further, I have 8 plus or minus the square root. 64 minus 16 leaves me with 48. over 8. Now, 48 would break down to, well, 4 and 12, which goes to 2 and 2, which is 2 and 6, which is 2 and 3. So out of this, I can pull one set, 2 set of 2s, and I have a 3 left over. So this would go to 8 plus or minus 2 and 2 would make 4 square root of 3 over 8, which I can reduce and get 2 plus or minus the square root of 3 over 2. And that would be my final answer. Now, the discriminant is that inside the square root part of it. So the b squared minus 4ac. Now, that alone tells us some stuff. So if the discriminant is positive, then we know we're going to have 2 real solutions. If we get a 0 there, we're going to have 1 real solution. And if it's less than 0, then we're going to have no real solutions. They're going to be 2 imaginary solutions. So, if you notice, we have the same thing right here. So that b squared was negative 8 squared minus 4 times 1, which we know was 48 from what we did up here. So that's where this is positive. So that means 2 real solutions. So if you think about it, if this was negative, then, or if this would equal 0, then we'd have the square root of 0. And so we're plus or minusing nothing. And so, like in that example, if this would have been a 0, we would just have 8 over 8, which is 1, and we get a single solution. Okay. Now, if it's, say, a negative 48, for example, well, then we would get our i's involved. It would be plus minus I of, well, 4i of 3. So that's where it goes to 2 imaginary roots. We're adding i's to them. So that's why when it's less than 0, we're no real, because we get 2 imaginary. If we're 0, we only get a single one. And then if it's positive, we get 2 real solutions, which 2 plus it, 2 minus it are 2 positive real solutions, or 2 real solutions. You don't necessarily have to be positive. So, when you're doing this, which technique do you use? Well, if we're in this deal, if it can be factored easily, factor it, use that zero product principle, get what x's are. If there is no constant, you still want to factor it. You want to pull out any common factors that you can, and then use the zero product principle. If it's in the form of ax squared plus c, so where we have no middle term, do your square root property. So add or subtract the c, whatever it is, to the other side, square root it, and get your deal. Same thing here. If it's in this form, we have something squared equals a constant, square root property. If it can't be factored easily, you can do quadratic formula. And that's whether it's just in this way, or if it has the c and it's not factored easily. So if you can't factor it easily, use quadratic formula. Now, radical equations are something else we can get into. So remember, radicals are roots. So whether it's a square root, cube root, fourth root, anything higher, if it involves a root in the equation, then it's a radical equation. So for example, if we have square root of x equals 9, that's a radical equation. So we would solve that then by squaring both sides. So if I have the square root of x equals 9 and I square both sides, that square root cancels. Well, the other side has to be squared as well. And so x would equal 81. Now, if we're going backwards, if we're squaring, getting rid of a square root, we don't have to worry about a plus or minus here. That's only when we're square rooting to solve that we need the plus or minus. So here, square it, cancel it, square it, boom, we're good to go. So when we have radical equations containing roots, so you want to get just the root isolated by itself on the one side. So have just a square root, a cubic root, fourth root, whatever it is, have just that on the one side, everything else on the other side if you can. Well, you have to, not even if you can, but you have to do that. Then you're going to square both sides to get rid of the square root, and then you can get x's on one side, other terms on the other, and then solve from there. Or if it's, say, an x squared situation, where it's a quadratic, get everything on the same side, do your zero product rule property after you factor it, and we'll go on from there. So let's do one. Let's do an example here. So first thing I do is I got to get this square root by itself. So I'm going to subtract the 2 over to the other side. So I have the square root of 2x minus 1 equaling x minus 2. So now I have just the square root by itself, so I can square it to get rid of it. Now this other side, when I square it, I'm squaring the entire side. Just don't distribute the square to each one. You have to FOIL that out when you do it, in this case. So 2x minus 1 equaling, if I FOIL this, x minus 2 times x minus 2, well, x and x would be x squared. X times a minus 2x. Negative 2 times x would be minus 2x. And then a minus 2 and a minus 2 would be a plus 4. So I'm going to get everything to the same side. Since the x squared is positive, I'm going to move everything to this side. So I'm going to subtract a 2x and add 1. So 0 equals x squared. Negative 2, negative 2, negative 2 would be negative 6x. 4 and 1 would be plus 5. So from there, can I factor it? You betcha. X and x. Because it's a plus, we look at here, so we got minus. So factors of 5, that would add together to be 6. Will be 1 and 5. So x minus 1 equals 0. And x minus 5 would equal 0. Well, add the 1 over. X equals 1. Add the 5 over. X equals 5. And that's it. That's this lesson. So, again, when you're going through these, if I'm going too fast and you need to pause it to write everything down, please do so. If you need to rewind it and hear something again, do that. Take advantage of this being a video and how you can watch it again or pause it and rewind and all that stuff. If you have any questions, comments, concerns, please pan me, email me, send me a message on Google Classroom. Any of that works. Otherwise, until next time, guys, we'll talk to you later.